In this video, we're going to talk about 3 common ways that a limit can fail to exist. And this is one of the things I think is really neat about calculus. In a lot of academic areas, if something doesn't exist, you just don't study it. But in calculus, we can say, this limit doesn't exist. In what way does it fail to exist? It's kind of cool. All right, so we've seen these 3 common ways. Now, I'm not claiming these are the only ways or the only reasons a limit might not exist. But the 3 common things that we've seen are that the function approaches different values from different sides. So we might have a graph that did something like this, that jumped. And it's not important whether we jump from a point to a hole, or a hole to a point, or a hole to a hole, or if there's maybe a point someplace else. It is important that along this vertical line here, there can only be at most one point. We are working with functions, so they have to pass the vertical line test. So we can't jump from a point to a filled-in point, because then we wouldn't have a function. We'd fail the vertical line test. All right, but here you can see we're approaching a y value up here from the left. We're approaching a y value down here from the right. So there we've got different values that we're approaching from different sides. Second thing that can happen is we could have a vertical asymptote. And with a vertical asymptote, we could have a picture that looks something like this, where the function is going up on both sides. We could have a function that looks something like this, where the function is going down on both sides. Or we could have a function that looked like this, where the function goes up on one side and down on the other. And of course, I could reverse that and have it go down on the left and up on the right. So lots of possibilities. Here we said the limit doesn't exist because it's not a unique number. Here we said the limit doesn't exist because it's not a number. I can say here we're going off to infinity, but infinity isn't a number. Here our y values are going off to negative infinity, but that's not a number. And here I actually have both problems. From the left we're going off to infinity, which isn't a number. From the right, we're going off towards negative infinity, which isn't a number, and which isn't the same thing as positive infinity. Okay, and the third way that we've seen that a function could fail to, a limit could fail to exist is, I'm just going to call it erratic behavior, or wild oscillations. So that was what we saw when we had y equals sine of pi over x, and we were trying to look at a limit as x approached 0. Okay. Wild oscillations might be a better name there, because it is, we can still describe what the function is doing. So it's not completely erratic behavior, but some functions will have erratic behavior. They'll just sort of be going all over the place. Okay. Now, this third one, we're not going to be able to do anything about. Okay, I can describe in words, oh, it's oscillating like crazy, but there is really no y value that we're getting close to and no way of describing what the function is doing, that it's heading towards a particular location. But both of these problems we're going to be able to do something about, because we do have things that we can say about describing the patterns that we're noticing. Okay. So, for that first problem of approaching different values from different points, we're going to introduce what's called a one-sided limit. Okay. let's just suppose that we've got some function f of x, and let's suppose that it looks something like so. So that at 1, we jump. And we jump from this point down here at a height of -1 to a hole up here at a height of 2. Well, certainly I can say if I come in from the left, as x gets closer and closer to 1, my y values seem to be getting closer to -1. I'm expecting there to be a point there. So that's going to be a one-sided limit. The way I'm going to notate that is I'm going to say the limit as x approaches 1, but I want to indicate that I'm coming from the left. I'm going to do that by putting a superscript here, and I'm going to put a superscript of a negative sign. In math, on our number line, the negative side of the number line is the left side, and the positive side of the number line is the right side. So I'm sort of using a sign here as a code for from the left. And then we would simply say of f of x, and in this case it would equal -1. Okay. So this just means as x gets close to 1 from the left, so x gets close to 1 from the left, y gets close to -1. And then, of course, I can describe the behavior from the other side. I would say the limit as x approaches 1. Now I want to say from the right. I'm going to put a little plus sign up there, and that's my code for right. And then we would say the limit, it's the limit of f of x, and that would equal 2. Now, do be careful here. If I'm approaching 1, an x value of 1 would be over here along this vertical line. If I'm a little bit to the left of 1, that doesn't necessarily mean my x values are negative. As I get closer and closer to 1, my x values will be positive. So this limit coming in from the left, that does not mean from negative numbers. It means from the negative side of the number line. Okay. But I can be to the left of 1 and still my x values are positive. We're just using the sign, the sort of code symbols, to mean left or right. All right. So those are our one-sided limits. Now, I can take one-sided limits even when two-sided limits exist. But here, I would say if I write this notation, we're talking the limit from the left, that's -1. If I use this notation, limit from the right, that's 2. If I just write the limit as x goes to 1 of f of x, if there's no superscript there to indicate that I'm coming from one side or the other, it's understood that that's a two-sided limit, and so this would not exist. Okay. And if I have a place, like let's say, well, let's just look at a different function. Let's say this is g of x. And let's say there's a hole here at the point 2, 1. Now here, I could take the one-sided limits. I could say the limit as x approaches 2 from the left of g of x. And then I just don't care what happens at 2 or to the right of 2. As I'm coming in from the left, I'm expecting there to be a point there. So this would be 1. That's the y value I'm expecting to get. The limit as x goes to 2 from the right, from the positive side of g of x. Now I'm looking here. I'm expecting there to be a point there. That would also be 1. Now, if these are the same, which they are, then I can now say that the two-sided limit of g of x is also equal to 1. And in fact, that's going to be a criteria for the two-sided limit to exist. The two-sided limit exists if and only if both one-sided limits exist and they're the same. Generally speaking, when a two-sided limit exists, we'll just go right ahead and talk about the two-sided limit. Where we need to use one-sided limits is when the one-sided limits exist, but the two-sided limit doesn't exist. Then we like to use those one-sided limits so that we can describe the patterns that we are seeing. But you're allowed to use a one-sided limit anytime, okay? It's just necessary to use that to describe the patterns when the one-sided limits are different. Okay, in the next video we'll talk about what to do if we have a vertical asymptote and extend a new definition of limit that's going to allow us to deal with those.